Good afternoon. Here is a short lesson on population and why we might want to estimate that population. So first up, what is a population? Maybe you were listening in lecture and maybe you already learned what a population is. For our purposes, a population is a group of interbreeding or potentially interbreeding organisms of the same species occupying the same space at the same time. This is important because if they're not interbreeding, that is no longer a population. Populations are dynamic. They're subject to changing, growth, loss. So without that population, without that interbreeding, it's not technically a population. They need to be the same species or else they can't be interbreeding. They need to be at the same place in the same time. So we talk about a population of rabbits in Australia versus the population of rabbits in Canada. We talk about the population of rabbits in Canada in 1950 versus the population of rabbits in Canada in 1990. The reason these are different populations is because they can't interbreed. If they're not in the same place in the same time, they are separated. I have a series of pictures that I usually show the class and ask you guys if you think this is a population or not. This is a group of deer, and we can argue that this is a population, but we can also argue that it isn't. Reasons it might be a population: they're all the same species, they're in the same place, in the same time. Are they interbreeding? Maybe. But arguments that they're not a population is that maybe they're not interbreeding. Maybe these are all females. Also, is this everybody? Or is this just a small portion of a larger population? So here we have multiple species of different fishes. It's not a population, it's a community. You guys remember community? This could be a population though. It's all the same species in the same place at the same time. I don't know enough about fish to know if they're all interbreeding or not, but it has better option than the previous one. Here are a bunch of shorebirds. They could be a population, maybe not. You guys figure that one out. Now, my favorite question is always why. Why do we want to know the size of a population? If we know the size of it, we can monitor the health over time. Is that population shrinking? Is that a bad thing? Is it growing? Is that a good thing? Or is it a bad thing that it's growing? How dense are they? Same number of individuals, but now in a smaller space. That's not nearly as healthy as those same individuals with more space. We can estimate our birth and death rates, find out how many are getting born and dying each year, which can really help. And if it's a species that we're harvesting, then knowing the birth rate and death rate and the population size year to year can help us regulate how many animals we're going to harvest. And as an environmental scientist, we really can't tell if these environmental issues are affecting these species unless we're monitoring them. How do we know if this new pollutant is affecting the population levels of the fish in a pond if we didn't already know the population levels of the fish in the pond before the pollutant was added? So by estimating our population regularly, we have a baseline that we can then compare to. There are different ways we're going to sample. So the first one's true census. This is a complete count of every single individual in a population. This is hard. There's not a lot of situations where we can do this. An example is in a farm or a zoo where we can actually count every animal in question, or on an orchard where we can count every tree. We can do this in seabird colonies where all of the birds nest all together. So that's that population of birds. And they might fly all over the place, but they always come back together to nest. We can do this with large mammals that are in open areas. So gnu on the savanna or caribou on the tundra, elephants. We can do this with organisms that aren't going anywhere. So trees, it might take a while, but you can count every tree in a forest because you can flag them as you go and you know they're not going anywhere. Indices are when we count small spots and then use that number to extrapolate to the whole population. So we do this regularly with birds and frogs and other animals that are noisy, and we stand in one spot and we listen and record what we hear. And then we take those numbers and extrapolate that based on the territory that we know they take up. If we hear this many in this space, and we know we might be able to hear them in between as well. We also do this with very regularly with plants. Plants don't really go anywhere. So we can set up a quadrat, a square, and count every plant in that small square. And then if there are 10 of those plants in a meter square, then we can use that to extrapolate how many are in a kilometer square, if the habitat is homogeneous. Mark recapture is when you have an animal population and you catch a few and tag them, and then you release them back into the population. And then you're going to catch them again, and the rate at which you catch recaptures is how we test what the population is. And there's a calculation I'm going to teach you on how to do that. We do this with small mammals, we do this with large mammals, we do this bird banding. You might have seen birds with bands. How many times do we recapture that same bird with the same band? Fish creel censuses are common. If you're an angler, you might have heard of those. In our lab manual, there are 3 different methods described: the Lincoln or Peterson method, the triple catch method, and the Jolly stochastic multiple recapture method. We're only going to practice and learn the Lincoln or Peterson method because it's the simplest, and I'm going to teach you the math for that in a different video. No matter which method you're using, when you're doing mark recapture, you're making assumptions. Those assumptions are in your lab manual. Here they are here. We are assuming that each marked individual is going to mingle randomly back with the rest of the population. That the act of marking it is not changing its behavior. It's going to go and do the same thing it always did. It's not changing the behavior of its peers. They're going to do the same thing it already did. They're not all going to clump together, all the marked crew. You're assuming that there are no losses, gains, births, deaths, emigrations between the time that you mark the original individuals and the time that you do your recapture. So you have to do some math and some studies before you start a mark recapture study so that you know what is the optimal time to leave for the organisms to mingle but not start dying. You're assuming that marking them does not change their behavior in any way, and you're assuming that each and every sample you take is taken randomly, that every individual in that population has an equal opportunity to be captured. This obviously doesn't always happen because we do get animals that are more likely to be curious and more likely to be caught, and animals that are shy and less likely to be caught. You do need the sampling period to be relatively small so that the time between sampling periods is no longer than the time it takes to actually do the sampling. And you're assuming that once they've been captured once, that they have the equal probability to be captured a second time as a critter that's never been captured before. So this is a problem with small mammals, is that some small mammals get trap addicted or trap shy. And we'll see this quite regularly. A small mammal trap is just a box with food at one end. And some mammals, just getting caught in that box is so traumatizing they will never go back. Other mammals, they're like, hey, free food, and they'll keep coming back again and again and again. So it's hard to do small mammal traps when you get trap addicted or trap shy individuals. So you're assuming when you do your math that you're not having those. And that's the end of our presentation.